Hello, class. Again, we left off with hexane, I believe. This is chapter 24, section 1, continuing with our hydrocarbons. Did get a little cut off last time, sorry about that. So this is where we left off here, talking about this one here, hexane, 6 carbons. Again, hydrocarbons, strictly carbon and hydrogen. This prefix here is telling me 6 carbons. Again, you need to memorize all of these prefixes. They will not be given to you as in methane means 1, ethane means 2. You just need to know those. So I would strongly suggest making index cards and having maybe, say, hexa on one side and on the other side the number 6 so you can memorize these. I will write up here also the endings, but we will get to the double and triple bonds soon. But here we have ane, meaning a single bond. Ene will mean a double bond. And ine will mean a triple bond. I will have you all stand up in class probably tomorrow, and we can do the ane, ene, ine bond dance. Oh, it's just so fun. We all look silly doing it, but trust me, you'll never forget it. But it's ane, ene, ine, 1, 2, 3. And that's a little dance we'll do in class. But ane again means single bond, ene means double, and ine means triple. All these, just a reminder, end in ane, so they will all have single bonds. We left off with hexane, so hexane, hex meaning 6, I'm going to first put my 6 carbons down. 1, 2, 3, 4, 5, 6. I will then attach my single bond because it ends in ane right here and have those attached. Let's start over here on the right. This carbon, once again, they all can have 4 pairs of electrons, 4 electron pairs attached to it, 4 valence electrons in the outermost energy level. So that's the carbon's capabilities. This one only has 1 pair attached here. I know it can hold 4 pairs altogether. So how many hydrogens can I attach to this carbon? 3. So now I have 1, 2, 3, 4 single pairs of electrons attached to that carbon, giving me 8 electrons in the outermost energy level. Again, that's what makes it the most stable. Let's take a look at this carbon here. How many is attached to it? 1, 2. I know I can have 4, so that gives me space to add 2 hydrogens. I am just filling it in with hydrogens where there is room. This carbon, 1, 2, attached with carbon bonds going on there, I have room to add 2 more to give me 4. 1, 2, I can add 2 more to give me 4. This carbon already has 1, 2. I can now add 2 to this one to give me 4. And don't forget this last one here. I only have 1 attached here. I need 4, so how many hydrogen am I going to add? 3. If you grow into each and every one of these carbons, you can see there has 1, 2, 3, and 4 bonds to this carbon. If I look at this carbon here, 1, 2, 3, 4, that they are sharing. These are shared electrons, okay? Sharing a single bond, a single pair of electrons at each of these sites, okay? If I were to write, say I was just given the structure, not the formula. Obviously I have the formula right here, but if I was just given this structure, I could write the formula. I would simply count the carbons, 1, 2, 3, 4, 5, 6. Count my hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And there I have my formula. If I were to just give you the structure and ask you to write the name, I would see that there is 1, 2, 3, 4, 5, 6 carbon. I would know that hexa is the prefix for 6, and They're all attached with single bonds there, so I would add an ANE at the end, giving me hexane. Let's try heptane. 7 carbons. 1, 2, 3, 4, 5, 6, 7. Ending in ANE, I'll attach my single bond right there. Start here on my end carbon. Only sharing one pair there. I need 4. I will fill it in with hydrogens. This carbon has 2, so I can add 2 more to give me 4. This carbon has 2, so I'm going to add 2 more to give me 4. This carbon, again 2. Going to add my hydrogens to give me 4. How about this carbon? 1, 2. This carbon, 1, 2. Add my 2 hydrogens to give me 4 pairs of electrons that are being shared. And this carbon here only has 1 attachment here. I have room to add 3 to give me 4 single bonds going on there. 4 single pairs of electrons. Octane, 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. Attach my single bond because it ends in A and E. And then I would go around just like we've done before and add all my hydrogens. Okay? Hopefully that is clear. We'll have lots of practice doing these, and hopefully this will all make a little bit more sense as you start doing these on your own. Okay? Again, these are all hydrocarbons, strictly hydrogen and carbon. I want to talk to you a little bit more about single bonds, which we just did. Okay? Anytime you have just single bonds going on, these are considered saturated bonds. In other words, they have the maximum number of atoms that can bond to it. They can be really long chain molecules, like we just did. They end in A and E because they are single bonds. So all your single bonded compounds, for example, all the ones that we just did, are saturated because they contain strictly single bonds. They do end in A and E. Some of these have what we call isomers present. This is a whole new word for you here, isomers. Okay, what that means, it could be compounds with the same formula but different structures. C4, what I have right, oops, sorry. C4H10, you know me in that pen, C4H10. This is both isobutane and butane. So C4H10 can mean same formula for both of them. Isobutane is C4H10, butane is C4H10. But structurally, they are completely different. Okay, I think I have those drawn on the next slide. But just once again, all these single bondeds are methane, ethane, propane, butane, pentane, hexane, octane are all saturated because they all have single bonds. They all ended in A and E, just like we just discussed, and saturated. Like we talked about in the last chapter, we talked about saturated. Remember, saturated solutions in the last chapter, maximum amount of solute that a solvent can dissolve. Well, here in bonding, it's the maximum number of atoms that can bond to it. And in this case, all our saturated bondings are single bonds and ending in A and E. Here are my isomers that I was just mentioning. We have isobutane and butane. Again, both are C4H10 right here. But structurally, isobutane is drawn like this. We have our 4 carbons, C4H10, 1, 2, 3, and 4 in isobutane. But this right here, like I have circled right here, is a branched chain. See how it just kind of shoots right off of there? Just kind of branched right off of there. But butane is a strict straight chain. Straight as an arrow. 1, 2, 3, 4 carbons and attached with our 10 hydrogens. Structurally, very different. They look very different. They're drawn different. But again, same formula, different structures is an isomer. And this is a great example of that, okay? Isomer. This, again, we talked earlier and I said you could have a chained structure. Here is a chained hydrocarbon, like almost like a paper loop chain, all in a straight line. This is chained. This is branched chain. You've got this little branch sticking off it, just kind of sticking right out, kind of random. Bang, right off the middle there. So that would be your branched. I think very easy to recognize. I give you a couple more here just for a visual. Again, straight chain, branched chain. I just didn't attach my hydrogens here just for sake of space. But again, this is your C4H10, and this would actually be a C4H10 also, your isobutane and your butane. A little bit here, more examples of your straight chain, branch, and now I want to throw in the carbon ring. Pull these names up. Here we have heptane, which we just drew a couple slides ago, okay? Here we have how many carbons? 1, 2, 3, 4, 5, 6, 7 carbons, okay? Now that I'm thinking about it, I think we skipped heptane. We went from 6 to 8. So this would be heptane. Actually, I did. I went from hexane to octane. We had the numbers right. I just, for some reason, skipped heptane. But here's your heptane. This hept right here. Oopsie, sorry. Hept meaning 7 right here. 7 carbons. ANE, which I have underlined in blue here, telling me that they are all single bonded. And this is how you would draw it. 1, 2, 3, 4, 5, 6, 7. I would draw my 7 carbons first. I would fill it in with my single bonds, and then I would attach my hydrogens accordingly. Straight chain. Isoprene, one that I won't be drawing a ton in class, but this is isoprene. Just to give you an example, I'm not going to talk in detail about this yet. I just wanted to show you what a branched chain looks like. Kind of like my isobutane has that random chain right here, branch just sticking right off of it, okay? And vanillin, which is like your vanilla that you use in cooking, is a ring. I will get into further detail on benzene rings soon, but you can see how each of these, whether it be your straight chain, branched, or ring, I think very easy to recognize. A ring, like it says, you have your ring here. This is considered a benzene ring. This is a symbol right here for benzene ring that you will be responsible soon to know, recognize, and draw. By itself is what I have written here. And then this whole structure here actually is vanillin, okay? Multiple bonds. Now we've talked about single bonds. Just going to talk just a little bit here about multiple bonds. Now these guys will either share 2 electrons at a single site or 3 electrons at a single site. Anytime you see that, these are considered unsaturated, unlike your single bonds, okay? If they share 2, the ending will be ENE, like I mentioned earlier. If they share 3, the ending will be YNE, ein. So, ein, ein. Ein was your single bond. En and ein, your multiple bonds. En, ENE, right, hold on, let me get my pen. Right here, sharing 2 and sharing 3 electrons at a single site. Let me just give you some names here so that you could fill these in. So all of these, the reason I have the 1 right here, hold on. 1, because they're all under an A and E. These will have double bonds. Oops, sorry. Oh dear. Because they all end in ENE. And here, I know these guys will share 3 electrons at a single site because they end in YNE. So actually very, very easy to recognize. So with the double bond,